This is the learning my work a lot notebook. I was like, I read this one. And there's certain things that, yeah, yeah. What did you, because I was thinking it. Well, that's why I can rip it out. Besides, like, I changed. Well, I know about you saying, like, you know, just in general, like. That's true. And that was very, like, dedicated, like, I had a primary book, I could make sure on this, I just put it in and make it very, like, you know what I mean? Yeah, it's organized. That's what I'm saying. I'm a bad bitch. Oh, I mean, for me, it helped. Like, no, it's when I was signing, and I believe in it all. I almost put my personal email. I was just like so gone. I was like, wait a minute. Wait a minute. I just keep remembering when my phone shows me. We have to type it out.
Okay, welcome back. We're starting 12 today. I should not have separated the handouts, but I did, so here we are. So we're gonna leave 11 like up in the air for now, and then we'll get back to it eventually. But I don't think he's putting 13 on the exam, so we're good. No 9?
Wait, I don't trust that. Wait, no,
I think it's 9.
Yeah, that's how I understand. That's right. I'm not sure. I could ask them. Yeah. Well,
We just asked email, he said it didn't be on time.
Okay, I mean, I don't know. It's good if you just know everything.
I would rather a little bit of mine.
Yeah.
Yeah.
Or half of 59 and then.
Okay. Huh? Maybe. Okay, so chapter 12, does this look familiar to you since you've seen it in class?
I mean, it's been a while.
It's been like 4 days.
No, I learned that.
Okay, that's fine.
Yes.
So yeah, chapter 12 is just redox, which is just going from carbonyls to alcohols back and forth. That's literally it. And there's just a few like sets of reagents and a few things you're gonna have to memorize. It's like the most simple chapter. So the very first part is like carbonyl reactivity, but we're gonna come back to that. Let's start with like redox. So what is reduction, and then what is oxidation? Reduction of oxygen. Okay, so reduction, you are reducing the number of oxygens, I guess. So in reduction, yeah, forget the electrons. So in reduction, we're increasing the number of hydrogens, or like increasing the number of bonds to hydrogen. Yes. So reduction, if there's like an increase of hydrogens or like bonds to hydrogen, I don't know, the molecule is reduced. And then knowing that oxidation is the exact opposite, what do you think happens in oxidation? You lose bonds to hydrogen and you gain bonds to oxygen. So you could be like increasing the number of oxygens, but like the increasing bonds is more accurate because like for oxidation, like going from an alcohol to a carbonyl, like this, like the number of oxygens is going to stay the same, but like the number of bonds to oxygen goes from 1 to 2. So knowing that on each of the reactions, like, is it a reduction or oxidation? So for the two arrows up on top, is it R or O? Yeah, it's going to be oxidation. So we're going from an alcohol, and then we're getting rid of some hydrogens and then replacing it with another bond to oxygen. So that's increasing, so this becomes oxidation. Also in general, like alcohol to carbonyl, definitely oxidizing. And then the second one is also oxidation. We're just replacing this H with like an oxygen. So you're just increasing number of bonds to O. So then on the way back from the carboxylic acid to the alcohol, what's happening? Yeah, the opposite, so reduction. So going from the carboxylic acid to aldehyde, we lose the oxygen. So we're increasing bonds to hydrogen. So there's more hydrogen reduction. And then literally the same thing for the last transition. So you get your aldehyde, you're adding like 2 hydrogens, definitely reduction. So the mechanism of reduction, any ideas? Yeah, that's literally it. So on a carbonyl, you have this carbon and this oxygen. The oxygen is electronegative, so it draws away electron density from this carbon. So this carbon becomes delta positive. And then being delta positive is going to make it electrophilic, right? Because it has less electron density. So because that carbon is delta positive, you can have all sorts of nucleophiles go in there and attack. And basically what just happens, you just add some random stuff onto the carbonyl carbon. So knowing that that's delta positive, when you have reducing agents, they're like kind of chunky molecules. And so it's like LiAlH4, NABH4. What it does, it turns a hydrogen into like an H- nucleophile. So this is connected to the reducing agent, and that just gives it like the bulk, so it can go in and do like an attack and add itself. But when we are reducing, like the actual part of the reducing agent that's doing the attack is the H-. So it's like often represented with just an H. So the H- from the reducing agent goes in and attacks the carbonyl carbon because the H- really sucks. It's really unstable and it wants to be stable by like binding itself to something. So that goes in, and then these electrons kind of like move up to accommodate the new hydrogen because you can't have 5 bonds on the carbon. And that's it. So now you get the same thing, but you have a hydrogen on the carbonyl carbon, and then these electrons go up to make it in alkoxide. So cool, you have your alkoxide. And then at the end of basically like every single reaction, we do something called an acid workup. So like whether it's written in the reaction line or not, you know you're gonna finish off the reaction with like H3O plus or H2O plus so that everything gets protonated and it's like happy. So H3O plus just goes in and protonates the alkoxide, the O minus, and you get this. You get a brand new alcohol. Okay, so knowing the mechanism is going to help us find the order of reactivity of carbonyls. So what do you think would make the carbonyl carbon more reactive? Having hydrogen bonds? And OH. No, because yeah, but why? Okay, so we said that carbonyl carbons react because they're delta positive. So we want the least electron density on those carbons. So what two things contribute to electron density? We have induction and also resonance. So first, let's look at the aldehyde. So this carbonyl carbon, we have the induction, like the electrons are going to the oxygen, it's great. And then from this R group over here, in general, I guess you should just like know this forever. R groups are electron donators, so they donate a lot of electron density to, I don't know, everything, mostly like electrophilic stuff. So the R group is actually donating electron density to that carbon. Not as much as the oxygen is taking away, but like it's doing something. So I should make the arrow shorter.
What's the goals like to be the
Most electron poor. So let me just write that. So less electron density is more reactive. So in aldehyde, we're pulling away a lot of electron density and we're contributing only a little bit. So this carbon is pretty delta positive. When we look at the ester over here, we can count the same things. So the oxygen is taking away density. The R group is donating a little bit, but one of the biggest factors here is this oxygen. So this oxygen is going to actually go in and do resonance. So you can do that, and then these electrons go up there. And what happens like with this resonance? So basically you're having electrons like buzzing between the two oxygens, right? And what comes between those two oxygens? This carbon right here. So like the electrons that are being shared between these two O's, they pass over the carbon. So that's more electron density, and we don't want that. So that makes it one of the least reactive ones. So because of resonance, the ester is not very reactive. So what do we think about the carboxylic acid? Would it be like similar or different? It's actually like literally the exact same. Like esters and carboxylic acids are, I think, considered basically the same reactivity. So we're just going to go ahead and say those are equal-ish. And then it's because of the same thing, like the oxygen goes in, does resonance, and you get a lot of electron density right on this carbon. So what do we think about the ketone then? The ketone is quite reactive, more or less than the aldehyde. Because it does have delta positive. So comparing the aldehyde and the ketone, they're practically the same, except you lose the hydrogen and replace it with another like hydrocarbon chain. So what's happening here is the exact same thing. Like the oxygen is taking away density, and the R groups, they contribute a little bit, right? The H doesn't contribute anything. The H has no electrons, so it's not going to induct anything. But these two R groups over here, they're contributing like twice as much as they are on the aldehyde, right? So even though it's a little bit of like more electron density, that the ketone is still like less reactive. Because it has twice as many hydrocarbons donating electron density. That makes sense, right? Okay. So what's the final order? Yeah. The first is aldehyde, second is ketone, and then ester and the acid are the same. Yes. So the aldehyde is the easiest to add stuff to, and then the ester car acid are the least easy to add things to. So knowing that, which of the carbonyls like would be the easiest to reduce into alcohols? The first one, yes. Why? Yeah, so it's the most reactive. And then in the mechanism for reduction, we're attacking the carbonyl carbon with the H minus. So we want something that like wants to accept that attack the most. And the aldehyde is the most reactive, so it's most willing to accept the hydrogen. So yeah,
The less electron, more reactive.
yes.
So why would the ketone be more active? Wouldn't it have more?
It would, so the ones in the middle have the most electron density because of resonance.
Okay. Oh, okay.
Yeah. Ketone has no resonance going on, just induction. So because of that like reactivity of the carbonyls, we have different categories of reducing agents. So our weak reducing agents are capable of reducing aldehydes and ketones. And they can be weak because aldehydes and ketones are very reactive. You don't need something like strong to force the reaction. And then whereas with a strong reducing agent, that is going to reduce all carbonyls, even the least reactive ones. So this is all you're going to have to memorize for the reagents of reduction. There's only two. So the first reducing agent is NaBH4. It's weak, and it only reduces aldehydes and ketones into alcohols. And the strong reducing agent is lithium aluminum hydride, LiAlH4, abbreviated LAH. Now reduces everything. Like aldehyde, ketone, carboxylic acid, ester, it turns everything into an alcohol. Okay. And then for redox, like this is basically what you're gonna have to remember. There's like a cute little chart on the last page, and it gives you like all the reactions simplified, and you can just like memorize them. So it's like what functional group reacted with a reducing or oxidizing agent, like what functional group is going to turn into what other functional group. It's like when you reduce an aldehyde, would you get a primary or secondary alcohol? What do you think? Primary, yeah. Because when we take an aldehyde and we attack it with H minus, like you only have one R substituent, and same on the aldehyde. So you just keep that one R and it stays as primary. And what about ketones? Ketones are secondary because when you attack a ketone, you have two R substituents, right? And you can't just like get rid of one of these carbons, like they're there forever. So all we can do is remove this bond to oxygen. For carboxylic acids, it's a little different. So I think in Orgo 1, you were told that like OH groups are never leaving groups or like rarely. In Orgo 2, they become leaving groups. So when we have a carboxylic acid and a reducing agent, the H goes in and attacks. And like, I don't know, either the first or second one. No, I got it. So it attacks, it kicks up these electrons. These electrons come back down. And when it comes back down to form the carbonyl, like you can't have 5 bonds, like it can't be bound to the H and still be a carbonyl. So like when this comes back down to remake the carbonyl, the OH leaves. I would like learn this pattern because it shows up literally everywhere with carbonyls. So you attack, these electrons go up, and then they come back down, ejecting the leaving group. Oh, I see, yeah. So what functional group is the result of that first step? Secondary alcohol, not yet. I heard aldehyde somewhere. That would be right. So all we're doing here, we're just like kicking off the oxygen and kind of like replacing it with an H. So for the first step of this kind of like mechanism, you are left with like an aldehyde intermediate. OH is gone, and then the carbonyl became like it got reformed, so it's still a carbonyl. So now I have an aldehyde. But you still have reducing agent in the solution. So like, are we done with the reaction? We're not. So we can continue by just attacking it again. So the H minus is still in solution. So it's gonna go back and attack the aldehyde because it's still really reactive. It attacks the aldehyde, it goes up, and then you get what functional group? Primary or secondary alcohol? Primary. So carboxylic acids give you primary alcohols because they have a leaving group. So like in the first attack, the leaving group leaves. In the second attack, like you get rid of the carbonyl and turn into an alcohol. And it's the exact same mechanism for esters because the OH and OR are like practically the same leaving groups. So esters form what functional group? Primary, secondary. esters? Yeah. Esters followed this exact mechanism, just replaced the OH with OR. And it was primary, so that ends with primary too. Let's see. Okay, so let's continue. I've taken some assorted carbonyls, and what we're gonna do is like pick either NABH4 or LiAlH4 to reduce these. So like which reagent would work on like each molecule, and then what would the final product be? So for the very first one, would we use NABH4 or LAH? Yeah, it's technically LiAlH4, but we say LAH because it's less of a mouthful. Yes, so LAH. Yes, because it can attack everything, including esters. So we use LiAlH4, and then it's going to turn into what as the final product?
The double bond's like knocked and it becomes like OH. And you have like the H to the side.
So an aldehyde at first, right?
Yes, it's not.
Like this?
You would have leftover oxygen as well, right?
Yeah, it's just like floating in the beaker. So yeah, this will be the first step of the reduction. And then the H minus is going to come back and reduce it further into a primary alcohol. So from these hydrogens down here that are attached to the carbonyl carbon, the very first hydrogen was used to like kick off the OR leaving group. And then the very second hydrogen was used to get rid of the carbonyl, to get rid of the double bond between the carbon and oxygen. And then, yes, you would have like the leaving group as some side product in solution, but no one ever asks about that. So the second one, what kind of carbonyl is it? A ketone, yeah. So what kind of reducing agent are we going to use? NABH4. So we use NABH4 because it's weak and it reduces aldehydes and ketones. And then what is this going to turn into? What does the ketone become? Secondary alcohol. So we keep everything the exact same because the NABH4 doesn't attack anything else. We just turn the carbonyl into an alcohol. Okay. The third one? Yes. So the third one, it's an ester, not very reactive. So we need something really strong. So we're going to take LiAlH4. It's going to come in and turn into a primary alcohol. So like the first hydrogen gets rid of this entire thing as the leaving group. So in the first step, we're left with like an aldehyde. And then that like benzyl alcohol is floating in the solution. And then the second step, we reduce the carbonyl. and we got our primary alcohol. Actually, oh, that's funny. So the leaving group and like the actual reduced ester are the exact same product. All right, what are we doing with this molecule? NABH4, because it's a ketone and it turns into what kind of alcohol? Secondary. So we just draw the exact same thing, but the ketone is now an alcohol.
Like we used NABH4 because it's more reactive.
The NABH4 is the weak reducing, so it reduces aldehydes and ketones. So like we could use the other one, but this one is better because it's less aggressive.
Another explanation, you were saying how like less reactive, so you use the stronger.
Yeah, but ketones are very reactive, so you can use the weak one. So what kind of carbonyl do we have here? So what are we using? Yeah. And it just turns into an alcohol. I'm not redrawing that whole thing. So we're just doing R OH.
What did you say was an aldehyde?
Yeah, aldehyde. Okay, very last one. What are we using? We have to use LEH because that's the only way we can reduce carboxylic acids. So cool, those turn into primary alcohols. For these, you could just memorize like what functional group it turns into, but you should be aware of the mechanism because sometimes he'll like give you NABD4 or LIALD4, and then instead of the H, you would have to like replace it with a D. Do you want to see an example? Okay. So let's say we had a carboxylic acid, and instead of LiAlH4, you were given LiAlD4. So instead of an H, what is doing the attacking? Yeah, so instead of an H minus attacking, you have a D minus attacking. So the D minus goes in, attacks the carbonyl. And in the first step, remember, it turns into an aldehyde. So in the first step, you're just getting rid of the OH. So this becomes like an aldehyde, but with a D. And then in the second step, the D minus comes back and gets rid of the carbonyl. So after the second step, the aldehyde turns into an alcohol. But one thing to be careful with is that in the last step, when it turns into an alcohol, like this proton up here that makes it an alcohol is still an H, unless told otherwise. So remember what I said about the workup, like whether or not it's written, it's there. And if it's not written, you can assume it's just like H3O as the second step. because the workup was done by H3O and the H is not a D. So the actual reducing agent has nothing to do with like protonating the alcohol. We need water or acid to come in and do that. And unless specified, so unless we had like D3O on the bottom, the alcohol would still be an OH. So if you're just given LiAlD4, NABD4, then like this would be your final product. But if like on the bottom line of the reagent, you're given like D3O or D2O, then the alcohol would also be a D. But in this case, we were not given that, so the alcohol stays in H. Okay, so that's like kind of like what most of the reactions and the problems are going to be like, but occasionally you might see something like this. So it's basically the same idea, except it's written out in condensed formula. So how would you go about doing this? Yeah, you would identify what functional groups are present. And a while ago, I think like sometime in chapter 9, I gave you like the condensed formula versions of all the carbonyls. Should do that again. So an aldehyde in condensed is CHO. Carboxylic acid in condensed is going to be COO. Or it could be COO or like CO2H. And CO2R is your ester. And CO is ketone. So with this, let's look at the first one. What functional groups are present in those formulas? So we have a ketone up here. That's obviously a ketone because the carbonyl is drawn out. And then the CO2R group is your ester. So if it was CO2H, it would be a carboxylic acid, but CO2CH3. So we know it looks like this. And then on the other side of the arrow, so our final product, what functional groups do we have? Yeah, so we just have two alcohols. So knowing that in the first one, we had a ketone and ester, and in the other side, we have two alcohols. What does that tell you? Yes, one of them is a secondary alcohol. That is true. Well, what does that tell you about what reagent we used? Yeah, okay. But we also reduced the ester, right? Yeah, exactly. So going from here to here, we had a ketone and ester. In the final product, both the ketone and the ester turned into alcohols. So both of them were reduced. And there's only one reagent that can do that. So only the lithium one can reduce both functional groups. So we had to have used the lithium. If we used never mind, we're getting to that.
the second example, is that why you said that?
Yeah, so, no, go tell me.
Because the second example doesn't have the primary alcohol, so that's why we use NA4.
Yeah, that's exactly right. So in the second example, we have the ketone and we also have the ester. But on the other side, in the product, we have the ketone turn into an alcohol, but the ester didn't. The ester is the exact same, right? Exactly. So you're right, it had to be NaBH4. So the NaBH4 is not strong enough to reduce an ester, which is why the ester stayed the exact same. How much time do we have? Okay, we can start talking about Grignards. So Grignards are a type of reduction, but instead of a hydrogen, you're adding like a hydrocarbon group. That's all the Grignard reaction is. So instead of like an H minus, like an LiAl or NaBH4 reagent, we have to use a separate Grignard reagent. So this is how you make those. So whenever you see like an alkyl bromide or an alkyl halide, like BrCl, whatever, and Mg over ether is what happens. The Mg is gonna like insert itself in between the carbon and bromine. So it literally just sticks itself between them. So you're just like turning the Br into an MgBr, basically. That's all. Nothing, it's just inert solvent. Ether is the most like commonly used solvent. It just like sits there and doesn't react with anything. So this MgBr, basically what it's representing is a carb anion. So what we can do, we can just like cut off the MgBr and like cut off that bond, whatever, and we're just going to replace that with a negative charge. So this propyl attached to an MgBr actually just represents a propyl with a negative charge on it. So in this case, this is the thing that's going to go in and attack the carbonyl. This is what's going to actually like do the reducing. So we call this the nucleophilic species. I've seen that occasionally, like this is why you should like be familiar with the mechanisms, because like he'll ask what is the nucleophilic species in the reaction. It's so you can like just think of it like as an ionic bond. So you can think of the MgBr as like a positive and then the carbon as a negative. So instead of like writing the MgBr, we can just like cut it off and imagine this.
So that's the same thing.
Yeah,
Go through each other.
basically. Huh?
Where's it gonna attack?
Carbonyls. Okay. So considering that this is the nucleophile, this is the nucleophilic species that does the attack, do you think this is nucleophilic, just nucleophilic, basic, or both? Why do you think that? Yes, I was thinking about that when I was making it. I was like, it's so obvious that it's both. But yes, it's both because remember the thing with bases? Like bases are usually negatively charged and they want to take a proton to like resolve that negative charge. So they hate that charge, especially the carbon. The carbon really hates the charge. So it wants a proton to come in and stabilize this and make it neutral. So it is both. So it is basic, and there's one specific case where it's going to act like a base. So if there is any acidic protons in the solution or reaction whatsoever, your Grignard is like gone, it's ruined, it's just going to attack that acidic proton. So it's going to act as a base when there is an acidic proton. It doesn't even have to be like an acid, like HCl proton. It could literally just be like water or an alcohol. So if you have H2O or an alcohol or like a carboxylic acid, like each time without fail, because the Grignard is such a strong base, it's so unstable, it's just gonna go and take all these protons and you're not gonna get the desired reduction that you wanted.
So basically, just want the reaction.
It will, it's just gonna make like a salt with these. And it's not gonna attack the carbonyl. Like if we had a carboxylic acid and then we gave it that Grignard, that propyl MGBR. So we can cut off the MGBR, get the anion. It's not gonna go in and attack the carbonyl like we would expect. It's just gonna go and take this proton. So now you're left with like a carboxylic acid. The O minus is like ionically bound to the MGBR part. And then this propyl has a brand new hydrogen and it's like very stable and happy. So you don't get the desired attack on the carbonyl carbon. You get this garbage.
Explain again,
Okay, so it's gonna act as a base because with Grignards, you have a negative charge on a carbon, which really sucks. Like you do not want charges on carbons. So the Grignard sees this acidic proton and like sees an opportunity to get rid of the charge. So the Grignard goes in and takes the proton and you get this product. So the Grignard gets protonated and it's really happy, it's neutral. And then as like a side effect of that, you get an O minus because the oxygen lost its proton. So to stabilize the O minus, you kind of glue the MGBR on it, which is positively charged. So the MGBR, like, it doesn't like float off in solution. It kind of just like stays ionically bound to the O minus, while this is the final product. Not the one we wanted, but the one we got.
Wait, which one's the final product? Which was the final product?
They're both,
Oh,
yeah. In this case, we care about the side product. That is all the time we have. If you're confused, I'll be here. But yeah, I'll see you tomorrow. Finishing this.